Okay, I would like to thank the organizers for inviting me and thank everybody for coming. Okay, probably my talk will be more an advertisement for bounded cohomology, in particular when dealing with negatively curved spaces or groups. I will speak about cup products just in the last 10 minutes probably because I'm not very interested in our recent results, but more on explaining what is going on with bounded cohomology for negatively curved spaces and why this could be interesting. So let me start with the definition of bounded cohomology of spaces. Today, I will stick to real coefficients, so we will only deal with chains and cochains with real coefficients. And once you have a topological space X, you consider the space of singular cochains with real coefficients, and we will denote it by that symbol. We want to single out bounded cochains. What does bounded mean in this context? So if you have a cochain, you can take the supremum of the values the cochain attains on singular simplices. So you have a lot of singular simplices with values in X, and you look at how the cochain behaves on these singular simplices, and you take the supremum. This is the L infinity norm of a cochain, and of course it may be finite or infinite, because there is no reason for which a cochain should have a uniformly bounded values on singular simplices, okay? But then by taking only cochains with a bounded L infinity norm, we define the subcomplex of bounded cochains, okay? It is very easy to check that the coboundary of a bounded cochain is itself bounded. So this is a subcomplex of the complex of singular cochains. And its homology, its cohomology, I should say, is just the bounded cohomology of X, okay? So bounded cohomology of a space is just something which is defined in a very similar way to standard cohomology of a space. But still, this small modification of the definition, which is we just consider bounded cochains, gives rise to a very different theory from standard cohomology. So let us start our comparison between bounded cohomology and classical standard cohomology. So first of all, the bounded cohomology of a point is just the same as the standard cohomology of a point, just because if the topological space is a point, you have, in any degree, in any dimension, you only have one singular simplex. So for sure, every cochain is bounded, okay? And moreover, this is probably more interesting, the bounded cohomology is still a homotopy invariant. So what's the difference between bounded cohomology and standard cohomology? We will understand this at least for some phenomena during my talk, but the point is whenever a construction in standard cohomology involves just a finite number of simplices, whenever a construction involves starting from a simplex and replacing it with a finite number of simplices, which is with this number uniformly bounded, then all the theorems which are proved this way should carry on to bounded cohomology. While all the constructions which involve taking one simplex and maybe subdividing it, but by a number of times which is not bounded a priori, then this could break things in bounded cohomology. The proof that standard cohomology is a homotopy invariant just involves taking a prism and subdivide it into tetrahedra or into simplices, and this can be done in a very controlled way from the point of view of the number of simplices involved. And this means that the standard proof that the standard cohomology is a homotopy invariant also works in bounded cohomology. Of course, bounded cochains include into standard cochains, and this induces a comparison map. This map is surjective when every standard cohomology class may be represented by a bounded cocycle, and this can be the case or cannot be the case. And it is injective, and this is a bit more subtle, when the following holds. If you have, let's say, a cocycle which is a coboundary of some maybe unbounded cochain, then it is also the coboundary of a bounded cochains. So injectivity of the comparison maps boils down to understand when primitives of bounded cochains may be chosen to be bounded themselves, okay? And this is usually not easy to understand, okay? Okay, so let's pass to the first differences between standard cohomology and bounded cohomology. For example, let's start by degree 1. So if we have a cocycle and we take any loop in our space, then by, for example, Jurevich's theorem, it is easy to check that if you apply the cocycle to the iterates of the loop, then we just obtain n times the cocycle applied to the loop. Okay, so if the cochain is bounded, of course, this implies that the cocycle should vanish on any loop. Because on the right-hand side of that quality, you see n times a number, which has to be bounded because gamma to the n is just one singular simplex, okay? So even if it wraps many times around the manifold, it is just one singular simplex. So if phi is bounded, it has to take a bounded, a uniformly bounded value on it. This shows that bounded cocycles vanish on any loop. And using so they admit a primitive. This is by the universal coefficients theorem, for example. And it is very easy in this case to check that this primitive is also bounded. And this implies that the first bounded cohomology module of any topological space vanishes. And this is a big difference with the usual standard cohomology. On the other hand, as I was mentioning before, subdividing simplices an arbitrary number of times is not a good behavior with respect to bounded cohomology. So the proof of the Mayer-Vittori sequence or of the excision theorem does not work in bounded cohomology. So we have vanishing of the first bounded cohomology model for every space, but we don't have Mayer-Vittori or excision. Sticking to the vanishing cases, if pi 1 of x is amenable, this is a deep theorem by Gromov in 1982, in the paper where he basically defined bounded cohomology for topological spaces, then the bounded cohomology vanishes in every degree. Okay? This is a very deep theorem. For example, the bounded cohomology of any simply connected space vanishes. Or of any torus. Any tori in every dimension have an abelian fundamental group. Abelian groups are amenable, so the bounded cohomology of any torus in any dimension vanishes. On the other hand, there are very simple spaces like the wedge of two circles for which the bounded cohomology is infinite dimensional, even in degree 2. So here we see two phenomena coming out of the lacking of Mayer-Vittori sequences. First of all, we have a one-dimensional cellular complex with non-vanishing bounded cohomology in degree 2. So the bounded cohomological dimension of a space, of a cellular space, may be bigger than the dimension of the CW complex, okay? Secondly, even if this is a finite CW complex, its bounded cohomology is infinite dimensional. So here we see that Mayer-Vittori cannot hold at all. What is more interesting no, not more interesting. Another interesting fact is that even in degree 3, the bounded cohomology of the wedge of two circles is infinite dimensional, okay? And most of my talk will be about these results and how to prove these results using differential forms on surfaces. So usually these results, for those who already know about bounded cohomology, is usually proved by the use of quasimorphisms and an algebraic approach to bounded cohomology, while today we will concentrate on a more geometrical approach. Okay, it's not very important for my talk today, but I think it's important to mention that also cohomology of groups can be defined, bounded cohomology of groups can be defined just by taking the usual resolution which computes the standard cohomology of groups and by restricting your attention to bounded cochains, okay? I'm not using the theorem of bounded cohomology of groups much today, so I will just say this. And there is a theorem by Gromov which says that for any CW complex, the bounded cohomology of a space is equal to the bounded cohomology of its fundamental group. When X is aspherical, then there are many proofs of this statement for aspherical spaces in the context of standard cohomology. And some of them can be just work also in bounded cohomology. So for aspherical spaces, this is not a surprise. But a deep result by Gromov ensures that this is true even for non-aspherical spaces, and this is quite astonishing to me at least. Okay, today we will speak about negatively curved manifolds, so everything will be aspherical, but I want to advertise this result, which is very important in the theory. Okay, as a consequence, the bounded cohomology of amenable groups vanishes in every degree, in every positive degree, and the bounded cohomology of the free group on two generators is infinite dimensional, both in degree 2 and in degree 3.
Is anything known in degree 4?
No. And I'm speaking about this problem in a few minutes. So let me just list some, why should we care about bounded cohomology? There are many reasons, but let me just mention two of them. One is because it's interesting in low-dimensional topology or in the topology of manifolds, because it is the dual theory of the theory of L1 homology. And from the L1 norm on homology, one can construct interesting invariants like Gromov's simplicial volume or the Thurston norm. It is a result by Gabay that the Thurston norm for degree 2 homology classes is equal to the Gromov norm. And computing the L1 norm of homology classes is quite difficult usually, and using the dual theory of bounded cohomology is of help. Another very different context in which bounded cohomology comes out is representation theory. Maybe here it's more important to focus on bounded cohomology classes for Lie groups, for topological groups. And when looking at representation from a discrete group, for example, into a Lie group, by studying the pullback of bounded cohomology classes on the Lie groups, one can construct invariants for representations. For example, Milne-Wood inequalities come out of from a similar approach. And there is a proof by Boucher, Burger, and Iozzi of most rigidity theorem, which uses bounded cohomology. And okay, many rigidity results can be obtained by using bounded cohomology. And I did not write this here, but also for people interested in geometric group theory, bounded cohomology is very related to the geometric group theory. We have seen that it vanishes on amenable groups, for example, on nilpotent groups, solvable groups, and it is very big for free groups. And these are particular cases of the general philosophy that bounded cohomology vanishes on positively curved or flat things, and is very big on negatively curved things. For example, it is infinite dimensional in degree true for many groups which are negatively curved. I will state some theorem in this spirit. Okay, today we will be more interested in hyperbolic manifolds. So let us start with surfaces. And for bounded cohomology, it seems, at least to me, that hyperbolic surfaces behave more or less like free groups. For example, the degree 2 and degree 3 bounded cohomology of surface groups is infinite dimensional. These are classical, by now classical results by Mitsumatsu and so on. Okay. And as I was mentioning 1 minute ago, this is true for negatively curved groups in a very general setting. It was proved, for example, for the first statement, which is the fact that in degree 2 bounded cohomology is infinite dimensional, was stated was proved for hyperbolic groups by maybe Epstein and Fujiwara. And then this result was extended for groups with negative curvature in more and more general, in more and more general meaning. And Hull and Ozin proved that this is true for acylindrical hyperbolic groups. And we proved with Maria Beatrice Pozzetti and Alessandro Sisto that also in degree 3 this is true, okay? In a very general setting. Acylindrically hyperbolic groups is a family of groups which contains, for example, non-elementary Gromov hyperbolic groups, mapping class groups, and many other interested groups in low-dimensional topology. Okay, so this answers the question. A very interesting and open problem is to compute the bounded cohomology of free groups, for example, in degree 4 and more. Nothing is known about this group. I mean, the first question, of course, is it vanishing or not? And we don't know. Okay? I should say that for many years, the feeling was that this should be very big, like in degree 2 and 3. But many vanishing results have been proved in the last year, so I would not push for one hypothesis or the other.
Is there any group where it's finite dimensional but not infinite dimensional?
Yeah, there is, and they were constructed ad hoc by Nicolas Monod. I think there are lattices in suitable groups. He proved that, basically, these lattices have no quasimorphisms, so their bounded cohomology is equal, basically, to the standard cohomology. And standard cohomology was finite dimensional, but non-zero. Okay, that was the proof. Okay, the same problem is there for surface groups. So it is not known whether surface group or surfaces have trivial or non-trivial bounded cohomology in degree 4 and more. And more in general, it would be interesting, at least to my eyes, to understand whether there could be a finite volume hyperbolic manifold of dimension n with non-trivial bounded cohomology in dimension n+1. This is true for surfaces, for example. We have just stated this result. And that's it. I mean, probably the most interesting case would be the 3-dimensional case, because if we can prove, if we can find a 3-dimensional hyperbolic manifold with non-vanishing 4-dimensional bounded cohomology, then we can probably prove that this is true also for surface groups and free groups. Okay, thanks to Hegel's virtual fiber ring theorem. Okay. So today, what are we going to do today? Basically, I would like to construct non-trivial classes by using differential forms. Okay, and this could maybe be of help also to study higher dimensional bounded cohomology for surfaces. This is the last. Of course, I have no results in this in this direction, but still, it's a strategy that could work maybe. So let's now study negatively curved manifolds, so pinched negatively curved manifolds. In fact, it is sufficient that the curvature of our manifold is bounded from above by a constant which is less than 0. We don't care about bounds, lower bounds. What is a straightening for M? A straightening is just an operator which takes a simplex and replaces it with another simplex, which is called straight, which is of class C1. And this is the important thing, that has a uniformly bounded volume, okay? So you start with the simplex, and you replace it with some other simplex, which should be thought of a geodesic simplex in some sense, which with a uniformly bounded volume, which depends on the, for example, on the dimension of the simplex, okay? I will describe a straightening shortly. Okay. This cannot be done in dimension in degree 1, because if you have a simplex whose vertices are very far, one from the other, then even if you straighten them, the length of the straight simplex you obtain will be unbounded, okay? Not uniformly bounded. But we all know that in the hyperbolic plane, triangles, geodesic triangles, have a uniformly bounded area, and so it is reasonable that you can do that in every degree, bigger than 2, bigger or equal than 2. We also need, unfortunately, a stronger property for straightenings, but I will call a straightening H strong if this, unfortunately, technical condition is satisfied, which is that in every degree between H and K, the norm of the P Jacobian of the straightened simplex is uniformly bounded independently of the simplex. What does this mean? For example, a straightening which is not strong just asks that the volume of simplices is uniformly bounded. Here we ask more. If you are straightening a 3 simplex, we are asking that the new map, the straightened map, at any point as a Jacobian, which is uniformly bounded on every orthonormal frame of cardinality between H and K. Okay? So we are not stretching too much the volume, but not only the top dimensional volume of the simplex, but also lower dimensional volumes. Okay? Of course, this cannot be asked in degree 1, because lengths can be as long as we want, but it can be asked in degree more than 2. Okay, what are examples of straightenings? Okay, first of all, and this procedure should be chain homotopic to the identity, of course. Of course, we cannot lose all the information on our simplices, okay? So how can we construct straightenings? First of all, we do not construct them in the manifold, but we construct them in the universal covering of the manifold in an equivariant way with respect to the covering automorphism group. And there are basically 2 important straightenings. The first one is the geodesic straightening, which was proved to be a straightening by Inoue and Yano in '82. And the second one is the barycentric straightening, which is originally due by Besson, Courtois, and Gallot, but then was used by a lot of authors, and like Chris Connell, Jean Lafont with Ben Schmidt, and Shivang, and maybe others that I'm forgetting now, and I apologize for that, in order to obtain estimates, for example, for the simplicial volume or for other invariants. Okay. I will explain what is the geodesic straightening because it's very elementary, and I will not explain what is the barycentric straightening because it is more complicated. So geodesic straightening is very easy. Here is the case of a 2 simplex, a singular 2 simplex with vertices x0, x1, x2. And we start from x0, x1, and we just take the unique geodesic joining x0, x1. Since M is negatively curved, its universal covering is a Hadamard manifold. In particular, it is uniquely geodesic. Between any pair of points, there is just one geodesic. And we parameterize it at constant speed. Then we take the remaining vertex, and we take the cone, the geodesic cone, from the remaining vertex to the first geodesic we had. And we can go on. If you have a three-dimensional simplex, then you take the fourth vertex and you take the cone from the fourth vertex to the triangle you obtain there. And in the manifold, you have a simplex downstairs. In the manifold, you just lift it in the universal covering, you straighten it, and then you push it down. And this is clearly invariant for the isometry group of the universal covering. So in particular, it is invariant for the covering group. And this defines a straightening on the manifold. And what Inoue and Yano proved is that in negative curvature, indeed, the simplices you obtain have uniformly bounded volume. Okay, the definition of barycentric straightening is more complicated, but at least for hyperbolic manifolds, we obtain the same objects. Here is a subtlety, which is important, that the barycentric straightening and the geodesic straightening for hyperbolic manifolds have the same image. So if you take a simplex and you apply these two different straightenings to the simplex, you obtain the same geometric object, but maybe the parameterization is different. Not maybe, it is different, okay? It is definitely different. Okay, and as I was mentioning, the geodesic straightening is a two straightening, and barycentric straightening has one less property because no one proved that it gives triangles of bounded area in dimension 2. This is likely to be true, but we won't need it. But the point is that it has this very important property that for the barycentric straightening, one is able to estimate the norm of the Jacobian also on orthonormal frames of dimension lower than the actual dimension of the simplex. Okay, and this will play a role in what follows. But we are able to give, unfortunately, it is not a too strong straightening, and we have counterexamples to this, okay? So in degree 2, also the barycentric straightening fails to control the norm of the Jacobian. Okay, how can we use the straightening to construct bounded cohomology classes? So let us fix a straightening on M, and we consider closed and bounded differential K-forms on M. What does bounded mean? It just means that a form is bounded if it is uniform, a K-form is bounded, if it is uniformly bounded on all K orthonormal frames on the manifold. For example, if the manifold is compact, then any differential form is bounded on it. If the manifold is open, then this means just that even going to the infinity, the differential form does not grow too much, okay? Once we have such a closed and bounded differential K form, we can just integrate it on a straight simplex. Okay, we have a simplex, we straighten it, and we integrate the form. And this map is well defined. Why? The point is that since straight simplices have a bounded volume, if we integrate a bounded class on a simplex of uniformly bounded volume, we obtain a uniformly bounded cochain, which is just what we need in order to define the bounded cochain, okay? The values this map attains on singular simplices is uniformly bounded, okay? And this is due basically to negative curvature. So negative curvature gives you a straightening, and a straightening with uniformly bounded volumes gives you the boundedness of this cochain. And since when you integrate a form on a simplex, this is independent on the parameterization, okay? So for hyperbolic manifold, geodesic and barycentric straightening give the same map because a new parameterization of the same simplex gives the same values. Okay. What is interesting here, for example, there is already a consequence of this construction that for closed negatively curved manifolds, every cohomology class may be represented by a bounded cocycle. This is because by de Rham's theorem, every cohomology class is represented by differential form. And by this construction, by straightening simplices and integrating differential forms, we obtain a bounded cochain. Since straightening is chain homotopic to the identity, basically we are just giving an explicit description of de Rham's isomorphism map. Okay. There is a theorem by Mineyev which says, for example, that the comparison map is surjective for every Gromov hyperbolic group, every non-elementary Gromov hyperbolic group. So this is a particular case of that theorem because we are dealing only with negatively curved manifolds. What is more interesting today is that there is this astonishing theorem by Bargengis, which says that if M is a closed surface, in degree 2, the map I introduce is injective. And this is quite strange because I'm taking all degree 2 differential forms because all of them are closed on surfaces, of course, because a surface has dimension 2, so all 2 forms are closed. And we are used to the fact that different differential forms give the same cohomology class if they differ by a coboundary. But here, even coboundaries, even exact forms, give non-trivial bounded cohomology class. This map is injective. The proof of this result is very clever, and it uses basically some ergodic theory of the geodesic flow on negatively curved surfaces. And recently, in particular, this shows that the dimension of this bounded cohomology group is infinite, because of course the dimension of the real vector space of 2 forms is infinite dimensional. And recently, Battista, Francaviglia, Moraschini, and Sarti extended this theorem for any closed negatively curved manifolds, but in degree 2. So the same statement is true in degree 2 for any negatively curved manifolds. And so this gives a lot of non-trivial bounded cohomology classes in degree 2 for any closed negatively curved manifold. Yes?
Could it also be surjective?
No. It's not surjective. There is a recent paper by Pietro Capovilla and Francesco Milizia and Federica Bertolotti and Giuseppe Bargagnati, I guess that's all, in which they study the action of the mapping class group on these classes for surfaces. And among the results they prove, there is one which says that not all the bounded cohomology of the surface is encoded by these classes coming from differential forms. Am I right? Okay. Unfortunately, in degree bigger than 2, this magic does not work anymore. And here, for closed form, which differ for an exact form, induce the same bounded cohomology class. But this gives rise, so we have a map between the usual de Rham cohomology of M and the bounded cohomology of M, which is still injective. But this gives at least introduces another interesting question. What is the image of this map? Because we always have the comparison map, right? The bounded cohomology always maps into the standard cohomology, while we don't have an inverse usually. This is an inverse to the comparison map, okay? is a right or left inverse. I will be wrong if I say right or left. Okay? And so the question is, it seems that we can choose a preferred element in the bounded cohomology module representing a standard cohomology class. And so what is this element? Has it any property which can be stated only looking at bounded cohomology, or we really need the differential structure or even the Riemannian structure on M to choose this element? So does it depend on the Riemannian structure, on the straightening? We don't know anything about this. Okay. So far we have considered basically closed manifolds. Let us pass to open manifolds and to open manifolds of infinite volume. We concentrate on this question, our attention on this question. When is the volume form non-trivial in bounded cohomology? Okay? So we have an open manifold, negatively curved, so we have the straightening with with uniformly bounded volumes of simplices. We integrate the volume form, so we just take the volume of simplices. This gives a bounded cohomology class. And the question is it trivial or not? This is a difficult question. And there is this conjecture by Gromov, which relates this question to the Cheeger constant of the manifold. So Gromov conjectures that this class is non-trivial if and only if the Cheeger constant of M vanishes, which means that the manifold contains compact submanifolds for which the ratio between the volume of the boundary and the volume of the submanifolds is going to 0. Okay? So we can basically exhaust our manifolds with bigger and bigger compact submanifolds with boundary, such that the volume of the manifolds, of the compact submanifold, is much bigger than the volume of the boundary of the submanifolds. Okay? We will see in a moment examples of this behavior. And, okay, Erwin Adziosmanovic, who is sitting here, has some partial results on this conjecture. Today we will discuss very easy cases in which this conjecture comes into play. For example, okay, I should say that Kim and Kim proved the conjecture for hyperbolic manifolds, not only three manifolds. This slide is incorrect. But we are sticking to a very easy case of infinite volume manifolds with vanishing Cheeger constant, which comes from manifolds fibering over S1. So this object has already come into play in this conference many times, so I will be not too slow on that. So what is a manifold which fibers over a circle? We can take M as a fiber of this fibering, take the mapping torus of M, which means we take M times 0, 1, and we glue M times 0 to M times 1 via a diffeomorphism of M. So this manifold has an infinite cyclic covering, which is diffeomorphic to M times R. Okay? R. It's just the infinite covering that you obtain associated to the fundamental group of the fiber. Okay? You have your manifold which fibers over the circle, you cut it open along the fiber, and you glue infinite copies of this M times 0, 1, and you have an infinite cyclic covering. This is the typical example of a negatively, if the manifold fibering over S1 is hyperbolic or negatively curved, then the same holds for the infinite cyclic covering, of course, which has infinite volume. And this is a typical example of a manifold with a vanishing Cheeger constant. Because you take, in this infinite cyclic covering, you take just the portion of the covering lying between M times 0 and M times I, and the volume of this compact submanifold with boundary grows linearly with I, while the area of the boundary is constant. Okay? And this means that the Cheeger constant of this manifold vanishes. And as a consequence, if M has dimension n plus 1, n, sorry, of course, since bounded cohomology is homotopy invariant, the bounded cohomology of M is the same as the bounded cohomology of this infinite cyclic covering. And if we believe in Gromov's conjecture, the bounded cohomology of this infinite cyclic covering should be different from 0, because this is a negatively curved manifold of infinite volume with vanishing Cheeger constant. Okay? The point is that for manifold fibering over S1, we don't need to believe in Gromov's conjecture, because there is a direct proof of this fact. I will give. This is the only proof of the talk, and it is very, very short. So we have, let us prove that for manifold fibering over the circle, when we take this infinite cyclic covering, the volume form of the infinite cyclic on the infinite cyclic covering is non-trivial in bounded cohomology. Okay? The reasoning is very. So we have this guy, and the monodromy here is just, if we take a point x here, the monodromy of this covering is just tau of a point x, and here we have, let t denote the real coordinate of points in this infinite cyclic covering, and this is just f of x t plus 1. Okay, this is the monodromy of the covering. And now we take a fundamental cycle for this fiber. You can take, for example, a straight triangulation. For those who are used to this sort of guys, you know that if the manifold fiber over the circle is hyperbolic, the fiber is very far from being geodesic. Okay, it is very pleated, but still you can take a straight triangulation, maybe with 1 million of simplices here. You call it Z. So Z is a cycle, a fundamental cycle. For m times 0. And then you take tau to the I of Z. This will be a fundamental cycle for m times I. Okay, so it will be here. So here we have Z. Here we have tau to the I of Z. And these ones, of course, are homologous in M times R, because they're just, they represent the same class in M times R. So their difference is the boundary of something, of an n plus 1 cochain. And so now, if the volume form, and this Ci is something which interpolates all this. Ci, the support of Ci should cover all this portion of the infinite covering, because its boundary is equal to this fundamental cycle minus this fundamental cycle. Okay? This means that if omega is the volume form, and so if omega is the coboundary of a bounded form, then we reach a contradiction, because omega of Ci grows. This is just the volume of m times 0I, more or less. So if we evaluate the volume form on the chain interpolating between Z and its translate, of course, if we evaluate this volume form on this chain in between here, we get something which grows as the volume of this region. But on the other hand, this is also the coboundary of B applied to Ci, and this is B applied to the boundary of Ci, which is just B of Z of tau I of Z minus B of Z. And this is bounded because this chain is fixed, is constant, and this one is obtained just by translating this chain, and it has the same number of simplices, okay? And since B is bounded, this value is bounded, this value is bounded, while this difference should grow linearly with I, okay? So this is a contradiction because this is bounded. And here maybe you see why Gromov conjecture that the key point is the vanishing of the Chigger constant. Because also in this proof is very easy, but because here we have much more than the vanishing of the Chigger constant. We have that the two boundary components of my compact submanifolds are related by a very simple transformation coming from the group of covering automorphisms of the manifold. So this is a very special case, okay? But still, the geometry of the Chigger constant comes into play, at least apparently. Okay. This already gives important consequences. For example, since there are three manifolds fibering over the circle with hyperbolic surfaces as fibers, this means that the H3 bounded of hyperbolic surfaces is non-vanishing just by this construction. A similar argument, if rather than using closed surfaces, we use a punctured torus, we can play basically the same game. And we obtain that H3 bounded of the punctured torus is non-vanishing, but the punctured torus has a free fundamental group. So we obtain also that H3 bounded of free groups is non-vanishing. And to my knowledge, the only non-trivial classes in degree 3 on free groups are constructed this way, or with variations coming from geometric group theory, but they are all based on this construction. So the fact that the three-dimensional bounded cohomology of free groups does not vanish only comes from these fiber rings. And that's the reason why we don't have any clue on how to promote this strategy to study the fourth bounded cohomology of free groups. Okay. So this is the open problem I was mentioning before. Is there a closed three-manifold M such that H4 bounded of M is different from 0? And maybe there is a very different strategy to attack this problem, but attacking it via fiber rings would put us in all the difficulties coming in when looking for four manifolds which fiber over a circle. Okay, there is some negative results in this spirit. So if a hyperbolic four manifold is homotopy equivalent to a closed three manifold, its Chigger constant is positive. So the strategy via Gromov's conjecture cannot work. Even if we are not looking to fiber rings, but we are taking maybe more complicated infinite volume hyperbolic four manifolds, we cannot find any of them which has vanishing Chigger constant. It is homotopy equivalent to a three manifold, okay? And the same for surfaces and free groups. So this strategy cannot be applied in the hyperbolic realm, okay? maybe in the negative, this is a theorem really about hyperbolic manifolds, not on negatively curved manifolds, okay? Okay, so in the last minutes, as I was promising, I will try to explain some strategies that people have tried to explore to produce non-bounded, non-trivial classes in degree 4, for example, using cup products. Okay, so first of all, cup product can be the cup product can be defined exactly in the same way as in the standard case, with the same formula, and it works. If you take the cup product of two bounded cochains, the resulting cochain is bounded, and all what we have to check for the fact that it is well defined and so on works in the bounded context. For example, the first open problem which comes into mind is the cup product the zero map? Since we don't know anything about H4 bounded of the free group, if H4 bounded of the group is 0, then of course this is the zero map. But people have tried to use the cup product starting from non-trivial classes in H2 bounded, because H2 bounded is huge, so you have a lot of classes, and you can try to take the cup product of these classes and see what happens. But unfortunately, a lot of results came out in the last years by Nikki Hoyer, Boucher, Monod, Francesco Fournier-Fascio, and Sofia Montova, and Michel Boucher. And they are all vanishing results, okay? So for many, many classes, this does not work. Let us try with differential forms then, okay? We take, there is this still negative result by Domenico Marasco, which says that for any exact form and every class, the cup product between any exact form, recall that if M is negatively curved, let's say enclosed, any exact form defines a bounded cohomology class. And in degree 2, these classes give only vanishing cup products with any other classes, okay? For the proof to work, you had to stick with exact forms, but this may be not necessary. And as a corollary, the cup product on surfaces vanishes on many, many pairs of classes, okay? Not all of them, because not all the classes are represented by differential forms, but still, this is a negative result. And the recent result I have with Francesco Milizia is one in the same spirit, so it is again a vanishing result. In fact, it is a different result which says that the cup product of classes coming from differential forms in degree at least 3, unfortunately, we have this condition, is vanishing in many cases. In fact, we prove a bit more. We prove that this map is a homomorphism of algebras. It takes the wedge product of forms into the cup product of bounded forms. But this already implies that this cup product is 0 in many cases. For example, if you are working on surfaces, you take the cup product of two differential forms. Of course, the wedge product of them is 0. And so the fact that this is a homomorphism of algebras says that the result is 0, okay? Okay, let me just say, so this is again a vanishing. There is a good point is that we don't have to stick to exact forms. This works also for non-exact forms. And we are able to prove a bit more that we have this nice homomorphism of algebras. A bad thing of our statement is that we need to take forms of degree at least 3. And this is a bit disappointing because the huge modus are in degree 2. And we feel that our proof should work also in degree 2. The problem is that we don't have a suitable straightening for the degree 2. It's just a very geometric, the difficulty is very geometric and is coming from the lacking of a good straightening. Let me just finish with the critical step. So how does the work prove? One, we all know that the wedge product correspond to the cup product for singular homology, okay? If you are not working in bounded cohomology. So one takes the one proof of this fact and check whether it works also in bounded cohomology. There are several difficulties. So one has to work with the approximation of the diagonal for the cross product and so on. But the most important one is this one, is that we need to show that if sigma 1 and sigma 2 are straight simplices, then this quantity is uniformly bounded. And so it is a very clear statement. And for this, we need a strong straightening. Remember, strong means that we have a control on the norm of the P Jacobian, where P is a lot of degrees. And we don't have such a straightening now. And so I will end with this question to you. Does a too strong straightening exist, at least for hyperbolic manifolds? If so, we can immediately promote our theorem to include degree 2 classes, because this is the only difficulty in our strategy. Okay, and that's it.